This is a quick lecture or discussion on topics to cover or to review for midterm 2. So I have on the screen here a short list of things to cover, and then I'll go through an example. So topics you want to make sure you understand. Well, first of all, let me just say that think of this as a review for the final more than anything. This isn't, I mean, we'll be covering material from most of the class, but this is so close to the final at this point that it's gonna, the final will be fairly similar. So yeah, think of this as a review for the final mostly. Topics to understand: perfect multicollinearity, basically just the assumptions of OLS for multiple regression. Multicollinearity was one of the assumptions. What is it? Why would it be a problem? Especially if it's perfect multicollinearity. That's basically when two variables are linear functions of one another. So an example would be if you have x1 and x2, perfect multicollinearity would be x2 equals, let's say, 10 plus 3x1. Okay, so x1 and x2 are perfectly correlated. They're just a line. Omitted variable bias, that's kind of been the topic of the class for the second half of the class after spring break. So I've covered this in many forms. So yeah, go and think about, let's see, conditions for omitted variable bias. So let's say omitted variable bias, things to think about, conditions. There are two conditions for omitted variable bias. One is that the omitted variable has to be correlated with the included regressor. So in our model, if this is our model, we're talking about things contained in U, right? So what's contained in U? If this is x1, x2 would be contained in U. The conditions would be that 1, correlation between x1 and x2 is not 0, and 2, x2 explains some of the variance in y. So x2 is an important predictor for y. If both these conditions hold, we have omitted variable bias, meaning the coefficient estimate on beta 1 hat of beta 1 hat, these estimates are going to be biased. So know what omitted variable bias is. Know how to test whether or not the effect of x on y depends on the level of x or depends on the level of z or some other variable. So this is basically interaction terms and nonlinear forms. So if the effect of x depends on the level of x, that means we want to have x squared in the model, or x cubed, or log of x. Or if it depends on the level of some other variable, maybe z, then that means we need to have z in the model plus an interaction between x and z in the model. So this is interactions between x and some other variable, and control variables, and then also nonlinear forms. You should know how to write down a hypothesis. So if you're, let's say, we've got a hypothesis in this model up here. Maybe our hypothesis is that beta 1, this is the null hypothesis, so we put a 0 there. Beta 1 is equal to 0 versus beta 1 not equal to 0, some other value. That's our null versus some alternative. We can also write down a hypothesis of beta 1 equal to 1 versus beta 1 not equal to 1. So our hypothesis is, we don't have to have it at 0, it's just that that's the convention. We typically are testing for 0 effect. So what's our t-stats in both scenarios? So t-stat for, let's call this h 1, and this is H2. So T1 is equal to beta hat 1 minus 0, because our null hypothesis is 0 over the standard error of beta hat 1. T2 is beta hat 1 minus 1, because our null hypothesis is 1 over the standard error of beta hat 1. So we could write down a t-stat to test both hypotheses. The hypothesis that beta 1 is equal to 0 versus 1. So just make sure you know how to do that. And also know of course, your rejection rule for your t-statistics. Then also r squared versus adjusted r squared. Remember that the r squared is always, well, let's say it this way. The adjusted r squared, which we write with adjusted r squared has a little bar over it, is always less than or equal to the regular r squared. This is a key thing to remember. The reason is the adjusted r squared adjusts for the addition of more variables in the model. What does the r squared mean and not mean? So go back to the notes and figure out things like, can we determine if we have the best model with an r squared? Can we determine statistical significance using the r squared measure? No, we can't. Does the r squared tell us whether or not variables are important variables to include in the model? Not really. The only thing the r squared really tells us is the fraction of the variance of y that's explained by the included x variables. All right, then finally, given a data set, this is probably the most important part, write down a model that tests the relationship between two variables controlling for two other variables. All right, so let me do an example of that. Okay, suppose I give you a data set, and the data set has, let me say, suppose I give you the data set with y, x1, x2, and x3. Just some random variables. We don't really even care what they are. But I say, let's say y is wages or income, and x1 is education, x2 is schooling. Well, actually, schooling and education would be the same thing. Family education. X3 is some other thing like ability. But I ask you, write down a multiple variable regression model that tests the relationship between y and x1 controlling for x2 and x3. So the question is, write down a model, population regression model, that tests the relationship between x1 and y controlling for x2 and x3. So how do you do that? Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus an error term. Our main variable of interest here is this one, x1, and these are our control variables. So this would be variable of interest. Now you suspect that the marginal effect of x1 depends on x2. So you think that the effect of x1 depends on x2, so write down a model to test this relationship, still controlling for x3. So how could you do that? You think the marginal effect of x1 in reality depends on the level of x2, so write down a model to test this. What would be your test? This should immediately, you should think interactions here. So marginal effect of x1 depends on level of x2. Okay, so how do we write down a model to test this? y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2. So that's going to be the test of whether or not the marginal effect of x1 depends on the level of x2. The test specifically is whether or not the coefficient on this interaction, beta 3, is equal to 0. And we still want to control for x3. We still want to have that as our control variable. So always remember when we talk about the marginal effects depending on the level of some other variable, that means we're looking for an interaction. Now write down a null hypothesis that the effect of x1 does not depend on the level of x2. Write down that null hypothesis. So that's what we just said. Null hypothesis is going to be beta 3 is equal to 0 versus beta 3 not equal to 0. Now write down a test statistic to test the null hypothesis from this regression, and figure out what criteria you would use to decide whether or not you can reject your null hypothesis. Okay, so the test statistic, of course, is going to be the t-stat because we're talking about one variable. Test statistic is going to be beta 3, and not that, beta 3, make that a little better, beta 3 hat minus the null over the standard error, beta 3 hat, which is equal to beta 3 hat minus 0 over the standard error of beta 3 hat, which is equal to beta 3 hat over the standard error of beta 3 hat. So those all come out in your regression output, and you can just determine whether or not you can reject the null straight from the regression output. What's our rejection rule for a t-stat? 95% confidence rejection rule. Reject if absolute value of the t-stat is greater than 1.96. Okay, now you suspect that the effect of x1 takes on a nonlinear relationship. In fact, you suspect that lower levels of x1 have very little impact on y, but as x1 increases, the effect of x1 on y increases. In other words, you think that the effect of x1 on y is increasing with the level of x1. So write down a model to test this relationship, still controlling for x2 and x3. So now we're basically saying the level of x1 depends, or the marginal effect of x1 depends on the level of x1. So that's a nonlinear model. How are we going to test this? Well, it's the easiest way to do this. There's several ways, all of which are fine. You could put in a squared term, a cubic term, or you could log x. And so let's do the simplest one. Let's put in a squared term. So let's do. Let me write down the question. The effect. You think the effect of x1 depends on the level of x1. So our test of this is going to be as follows. So that's probably the simplest way to test this. We've just added a squared term here for x1. And so we can specify a null hypothesis that the effect of x1 does not depend on the level of x1, and that null hypothesis, of course, would be beta 2 equals 0 versus beta 2 not equal 0. I'll write that a little better. Beta 2 not. Okay, suppose you estimated both of these models. You estimated the one in which you're testing whether or not the marginal effect of x1 depends on the level of x2, the model written here. And you've written down this null hypothesis. You get a t-stat of, let's say, 3.5. You can then compare that to 1.96 for your rejection rule. So we would reject the null hypothesis if our t-stat was whatever I said it was. And that would mean that we should have this interaction term in the model, the interaction between x1 and x2, because it's important. Beta 3 is statistically significant, suggesting that that interaction is important, and the marginal effect of x1 depends on the level of x2. On the other hand, if we then tested whether or not the marginal effect of x1 depends on the level of x1 using this other model, then and we found that the t-stat on beta 2, we found that the t-stat on beta 2 was 1.4. We would fail to reject the null hypothesis. So beta 2, this nonlinear effect does not seem to be important, suggesting that there is no relationship between x1 squared and y, or at least it's not a statistically significant relationship. So we don't need x1 squared in the model. Okay, next I'm going to introduce some dummy variables. So suppose you have data on, let's just say, wages and education, and a dummy variable for male versus female. And you want to test whether the effect of education on wages is different for males versus females. Okay, so we have wages, we have education, and we have a dummy for 0 females, let's say, and 1 males. Now, first of all, let's say we want to test whether or not males and females have different wages on average. So how would we do that? Well, the first model we would write down then is wages equals beta 0. We're going to control for education, and we're going to put in the dummy variable. So all that dummy variable there is doing is just saying that we think the effect of, or we think that males and females have different wages on average, controlling for education. Or alternatively, we could say we're testing the relationship between education and wages, controlling for male and female dummy. But the question of interest is you want to test whether the effect of education, the marginal effect of education on wages is different for males versus females. So of course, if we're going to talk about the level of one variable being affected by the level of another variable, we need an interaction term. So we would have a model that looks like this. We need this interaction term in the model. Whoops, that's not supposed to look like that. Let me write a better D. Beta 3 education times that dummy there. So this variable here, or the interaction term, is going to be the test of whether or not the effect of education depends on this male versus female dummy. Okay, now suppose you estimate this regression and you get the following sample output. Let's say you get 5 plus 1 times education plus 2 times the dummy plus, let's say, I don't know, 0.5 times education times the dummy. So that's our sample output. So it might ask you questions like, what are the expected wages for females with 10 years of education? So let's figure that out. All right, so we have females. This dummy is equal to 0 for females. So if we're talking about females, then this term over here is going to drop out, and this term is going to drop out. So I said females with 10 years of education. So the only thing that matters here is going to be the remaining terms, the intercept, and education. So we would have, we can write expected wages conditional on females and education equals 10 years. That's going to be equal to 5 plus 1 times 10 equals 15. Wages are going to be $15 per hour, if that's our units of wages. How about the expected wages for males with 10 years of education? Okay, so in this case, the dummy is going to be turned on because males is D equals 1. So now we're going to write expected, what color should we do this in? How about, we haven't done black. Expected wages for not females, for males with education equals 10. So that's going to be 5 plus 1 times 10 plus 2 times 1. So we're substituting the 1 in for D up here, because D is now equal to 1, plus 0.5 times 10 times 1. So what does that give us? And hopefully I don't do this wrong. That's going to be 5 plus 10 plus 2 plus 5. So it's going to be 22. $22 per hour. So on average, with 10 years of education, men are making $7 more per hour than women, according to this regression output. Now sketch a graph of the relationship between education and wages for men and for women. Now this graph should have two different lines, one for men and one for women, and label the y-intercepts and the slopes. So the first thing we need to do is figure out what that regression line looks like when D is equal to 0 for females. So we're going to have wages hat conditional on, let's put expected wages hat conditional on D equals 0. That's going to be 5 plus 1 times education. And then these other two terms drop out. The D times 2 drops out because D is equal to 0. And 0.5 times education times D drops out as well. Now what does this regression line look like when D is equal to 1? Expected wages conditional on D equals 1 is 5 plus 1 times education plus 2, because D is equal to 1, so I'm just dropping the 1. Well, 2 times 1 is equal to 2, plus 0.5 times education. Again, D is equal to 1, so I can drop that. Okay, so then let's simplify this a bit. We can sum up the intercept. So 5 plus 0.5 is 5.5. And then the slope of the line is going to be 1 times education plus 0.5 times education. So we'll get 1.5 times education. Okay, so now we have two different lines. One for the relationship between wages and education for females, and the one for the relationship between education and wages for males. And so we can draw those. Let's do that real quick. Okay, so now we know we have, all right, we have to label the X and Y axes. So this is wages. This is education. Our intercepts, well, let's do the intercept for, let's draw the female line first. So our intercept here is 5. Put that there. Say that's 5. The slope of this line is 1. Doesn't really matter so much how I do this. Let's say that's a slope of 1. Now let's do the male line. So, well, first of all, let me write this out. So the slope here, slope is equal to beta, forget which one that is, beta hat beta 1, which is equal to 1. So the slope is equal to beta hat 1, which is equal to 1. Intercept is beta hat 0, which is equal to 5. Now let's do the male line. So now we have, this is our intercept, and this is our slope. Okay, so now that intersects right there. Call that 5.5, which is beta hat 0 plus beta hat, what is it, 2? Yeah, beta hat 2. And the slope of this line is slightly steeper than the slope of the previous line. Maybe ever so slightly. So it's going to look something like this. So now we can write slope is equal to beta hat 1 plus beta hat 3. Okay, so this is the male line, and this is the female line. So you should be able to do that for different coefficients or different, just generally, if you have a dummy variable in the model, you should be able to draw out these lines. Other things you should think about studying for the midterm: how to assess multiple regression studies. Should we be, if you want to compare different models, if you want to choose an appropriate specification, do you want to include, how do you determine if you want to include different control variables? How do you determine, that's going to be omitted variable bias. How are you going to determine if you want to have a nonlinear form or if you want to have an interaction term? We've talked about that a bit. But we haven't specified formal tests of this or joint hypothesis tests for multiple coefficients in this review, but we have covered that in the class. So think about if we have multiple variables in their model that we want to determine are they important or not, we would use a joint hypothesis on those multiple variables, and then the appropriate test for that would be an F statistic.